Right now, at this very moment, while you sit here watching this video, something extraordinary is happening in a region of space so distant, so incomprehensibly far from Earth, that the human mind cannot truly grasp it. There is an object out there, a small, fragile, human-made machine, no bigger than a compact car, hurtling through the absolute void of interstellar space at over 38,000 miles per hour. It has no pilot, it has no crew. It carries no weapons, no cargo, no supplies. What it carries instead is something far more profound, a golden record etched with the sounds of our world, the music of our civilizations, greetings in 55 human languages and encoded images of life on Earth. It carries, in the most literal sense imaginable, a piece of who we are. And right now, that tiny emissary of humanity, that impossibly brave little spacecraft, is more than 15 billion miles from the planet that built it. 15 billion miles. Let that number settle into your mind. If you could drive a car at highway speed toward Voyager 1, it would take you over 25 million years to reach it. If you shouted into the void and somehow your voice could travel at the speed of light, it would take over 22 hours for that sound to arrive. 22 hours at the speed of light. That is where Voyager is right now. Alone, in the dark, in the cold. In a place no human has ever seen, no telescope has ever resolved, and no other machine has ever reached. And it just sent us a message. A faint whisper, carried on radio waves so weak that by the time they reach the antennas of NASA's Deep Space Network on Earth, they carry less energy than a billionth of a watt. A signal so feeble that it is literally 100 billion times weaker than the power of a single watch battery. And yet, we heard it. We decoded it. We analyzed it. And when scientists looked at what Voyager was telling us, when they studied the data streaming in from the absolute edge of our solar system and beyond, something changed in the room. Something changed in the equations. Something changed in our understanding of where we live, how protected we are, and what the universe really has in store for us. Because Voyager did not send back good news. Voyager confirmed something that a growing number of scientists had been quietly, cautiously, almost reluctantly suspecting for years. Something that many of them had hoped would turn out to be wrong. Something that, if you truly understand its implications, should fundamentally alter the way you think about our place in this galaxy. What Voyager found at the edge of the solar system is not just a scientific curiosity. It is not just a data point for academic papers. It is a revelation about the nature of our cosmic home, about the fragility of the invisible shield that protects every living thing on this planet, and about the vast, powerful, and deeply indifferent forces that press against us from the depths of interstellar space. What if everything we thought we knew about the edge of our solar system was wrong? What if the boundary between our sun's domain and the galaxy beyond is not the strong, stable, protective wall we imagined? What if the shield that deflects deadly cosmic radiation, the bubble that has sheltered life on Earth for billions of years, is thinner, weaker, more porous, and more vulnerable than anyone wanted to believe? What if the galaxy outside is not the passive, quiet void we assumed, but an active, pressing, relentless force that is constantly testing our defenses? And what if Voyager, our most distant messenger, the farthest thing humanity has ever built, just confirmed all of this? These are not hypothetical questions anymore. These are not speculations or fears or worst-case scenarios. As of the latest data returned by Voyager 1 and Voyager 2, these are established scientific realities. And today, in this video, we are going to take a journey through the entire story, from the very beginning to the very latest findings, and we are going to understand exactly what is happening at the edge of our solar system, why it matters, and what it means for the future of every living thing under our sun. But before we can understand what Voyager found, before we can grasp why scientists are calling this data disturbing, before we can truly appreciate the magnitude of what is happening 15 billion miles away, we need to go back. We need to go back nearly 50 years, to a time when Voyager was just an idea, a dream, a wild ambition born from a once-in-a-lifetime cosmic coincidence. Because the story of Voyager is not just a story of technology or engineering. It is a story of timing, of luck, of human stubbornness, of political battles fought in the halls of Washington, and of a rare alignment of planets that happens only once every 176 years. If you find yourself amazed by the idea that a machine launched in 1977 is still functioning in interstellar space, sending back data that is rewriting our textbooks, then the story of how that machine came to exist in the first place will absolutely astound you. Because Voyager should never have been built. It almost wasn't. And the fact that it exists at all is one of the most remarkable accidents of timing in the history of human exploration. It was the late 1960s. The United States was in the grip of space fever. The Apollo program was in full swing. Astronauts were preparing to walk on the moon, and the American public's imagination was soaring beyond anything that had come before. In the midst of this excitement, a young aerospace engineer at the Jet Propulsion Laboratory in Pasadena, California, named Gary Flandreau, was given what seemed like a routine assignment. His job was to study possible trajectories for future missions to the outer planets, specifically Jupiter, Saturn, Uranus, and Neptune. These were the giant worlds of our solar system, mysterious and poorly understood, orbiting so far from the sun that reaching them with the rocket technology of the day seemed almost impossible. A direct flight to Neptune, for example, would take over 30 years with the propulsion systems available. It was, by any practical measure, unfeasible. But Gary Flandreau discovered something that would change everything. As he plotted the orbital positions of the outer planets into the future, he realized that in the late 1970s, a rare and extraordinary alignment would occur. Jupiter, Saturn, Uranus, and Neptune would all be arranged on the same side of the Sun, in a configuration that would allow a single spacecraft to visit all 4 planets by using a technique called gravity assist. The idea behind gravity assist is elegantly simple but profoundly powerful. When a spacecraft flies close to a massive planet, it can use that planet's gravitational pull to accelerate and redirect its trajectory, essentially stealing a tiny amount of the planet's orbital energy to fling itself toward the next destination. By carefully timing the encounters, a spacecraft could hop from Jupiter to Saturn to Uranus to Neptune, gaining speed at each stop, covering in 12 years what would otherwise take 30 or more. It was a cosmic billiard shot of breathtaking precision. And here was the critical part. This alignment of the outer planets happens only once every 176 years. The last time it had occurred, the year was approximately 1801. Thomas Jefferson was the President of the United States. Napoleon was consolidating power in France. The steam engine was a crude novelty. The idea of sending a machine to another planet existed in no human mind anywhere on Earth. And the next time this alignment would occur after the 1970s, roughly the year 2153. No one alive in the 1960s would ever see another opportunity. No one alive today will ever see another opportunity. This was it. This was the moment. Gary Flandreau knew it immediately, and he raced to tell his colleagues and superiors at JPL. The result was a proposal that NASA called the Grand Tour, an ambitious plan to send multiple spacecraft on trajectories that would take advantage of this once-in-multiple-lifetimes alignment to explore all 4 giant planets in a single, sweeping journey through the outer solar system. The Grand Tour concept was breathtaking in its ambition. It called for pairs of spacecraft to be launched on different trajectories, providing comprehensive coverage of all 4 giant planets and their major moons. The scientific potential was enormous. At the time, we knew almost nothing about these worlds. Jupiter was a striped giant with a mysterious great red spot. Saturn had rings that we could barely resolve. Uranus and Neptune were little more than fuzzy dots in our best telescopes. The Grand Tour would transform these distant abstractions into real, tangible, understood worlds. It would be, without exaggeration, the greatest voyage of exploration in human history. But there was a problem. A very large, very mundane, very human problem. Money. The Grand Tour, as originally conceived, was going to be expensive. Very expensive. And by the early 1970s, the political and economic landscape of the United States had shifted dramatically. The Vietnam War was draining resources and public patience. The economy was struggling. The initial euphoria of the space race was fading. NASA's budget, which had peaked during the Apollo years, was being slashed year after year. Congress looked at the price tag of the Grand Tour and said no. The program was canceled. Just like that, the greatest exploration opportunity in 176 years was being thrown away because of budget constraints. Scientists at JPL were devastated. They knew what was at stake. They knew that this window would close and never reopen in any of their lifetimes. And so, they did what scientists and engineers often do when faced with impossible bureaucratic obstacles. They got creative. They redesigned the mission. They scaled it down. They simplified it. They found ways to cut costs without cutting ambition entirely. And what emerged from this process was a leaner, more focused mission that could accomplish most of what the Grand Tour had promised, at a fraction of the cost. This redesigned mission was given a new name, Voyager. 2 spacecraft would be built, Voyager 1 and Voyager 2. Both would visit Jupiter and Saturn. Voyager 2 would be placed on a trajectory that could, if the spacecraft survived long enough and performed well enough, continue on to Uranus and Neptune. Voyager 1, on the other hand, would be aimed at a special close encounter with Titan, Saturn's largest moon, which was known to have a thick atmosphere and was considered one of the most scientifically intriguing objects in the solar system. This close flyby of Titan would bend Voyager 1's trajectory out of the plane of the solar system, ending its planetary tour, but sending it on a path that would eventually carry it toward the stars. At the time, no one fully appreciated the significance of that trajectory. No one realized that Voyager 1's deflection away from the planets would ultimately make it the first human-made object to leave the solar system entirely and enter interstellar space. That was not part of the plan. The plan was to study Jupiter, Saturn, and if they were lucky, Uranus and Neptune. Everything that happened after that was a bonus. A magnificent, world-shaking, fear-confirming bonus. The engineering challenges of building Voyager were staggering. These spacecraft would need to operate for years, far from the sun, in the coldest, most hostile environments ever visited by any human-made machine. They could not rely on solar panels for power, because at the distance of Jupiter and beyond, sunlight is so dim that solar panels would be practically useless. Instead, the engineers at JPL equipped each Voyager with 3 radioisotope thermoelectric generators, or RTGs. These devices generate electricity from the heat produced by the natural radioactive decay of plutonium-238. They have no moving parts, require no maintenance, and produce a steady, reliable stream of power that decreases slowly over time as the plutonium decays. When Voyager launched in 1977, Each spacecraft's RTGs produced about 470 watts of electrical power, roughly enough to power a few household light bulbs. That was all the power available to run every instrument, every computer, every heater, every motor, and every communication system on board. And by now, nearly 5 decades later, that power output has dropped to around 200 watts. The engineers have had to make agonizing decisions about which instruments to keep running and which to shut down forever, carefully rationing every precious watt as the plutonium slowly, inexorably dies. The computers on board Voyager are, by modern standards, almost laughably primitive. Each spacecraft carries 3 computers: the computer command system, the flight data system, and the attitude and articulation control system. Together, these 3 computers contain a total of about 69 kilobytes of memory. That is not a typo, 69 kilobytes. Your smartphone has millions of times more computing power. A modern digital greeting card that plays Happy Birthday when you open it has more memory than the entire computer system that is navigating Voyager through interstellar space. And yet, these simple, elegant, brilliantly designed computers have been functioning for nearly 50 years, executing commands sent from over 15 billion miles away, managing spacecraft systems, processing scientific data, and making autonomous decisions when communication delays make real-time control impossible. They are, in their own way, one of the greatest engineering achievements in human history. The communication system is equally remarkable and equally humbling. Voyager's main radio transmitter operates at a power of approximately 23 watts. 23 watts. That is less than the power consumed by a typical refrigerator light bulb. And yet, that 23-watt signal, transmitted through a 3.7-meter high-gain antenna dish, travels across 15 billion miles of empty space and is picked up by the massive 70-meter antennas of NASA's Deep Space Network on Earth. By the time the signal arrives at Earth, it is spread out so much that the received power is measured in attawatts, 10 to the minus 18th watts, a number so small that it is almost meaningless in everyday terms. The fact that we can detect, receive, and decode this signal at all is a testament to the extraordinary sensitivity of the Deep Space Network and the precision engineering of Voyager's communication system. Every data bit sent by Voyager crosses the void at the speed of light, taking over 22 hours to make the journey. When scientists on Earth send a command to Voyager and wait for a response, the round-trip communication time is nearly 2 full days. It is like having a conversation with someone where every reply takes 44 hours to arrive. And then there is the golden record. If Voyager's engineering represents the best of human ingenuity, the golden record represents the best of the human spirit. It was the brainchild of Carl Sagan, the astronomer, author, and perhaps the most gifted science communicator who has ever lived. Sagan chaired a committee tasked by NASA with designing a message that would travel with Voyager into the cosmos, a message that might, someday, millions or billions of years in the future, be found by an extraterrestrial civilization. The result was a 12-inch gold-plated copper phonograph record, enclosed in an aluminum cover with symbolic instructions for how to play it, along with a stylus for playback. The record contains 115 encoded images showing life on Earth. Natural sounds including wind, thunder, birds, whales, a heartbeat, laughter, and a mother's kiss. Musical selections from around the world spanning centuries and cultures, from Bach to Beethoven, from Javanese gamelan to Blind Willie Johnson's haunting "Dark was the night, cold was the ground," and spoken greetings in 55 different human languages, from ancient Sumerian to modern Mandarin. There is even a recorded greeting from a child, a young Nick Sagan, Carl's son, saying, "Hello," from the children of planet Earth. Sagan knew, and said so explicitly, that the chances of the golden record being found by anyone were essentially zero. Space is too vast, Voyager too small, the distances between stars too enormous. The record was not really a practical communication device. It was something else entirely. It was a statement of intent. It was a declaration of hope. It was humanity saying to the universe, "We are here, we exist, we think, we feel, we create, we love, we dream." And even though we are small, even though we are mortal, even though our world is just a pale blue dot in an ocean of stars, we had the courage to send a piece of ourselves into the infinite. That is what the golden record represents. And it will outlast every human being alive today, every building, every city, every nation, every monument, perhaps even the Earth itself. Long after the sun swells into a red giant and consumes the inner planets, Voyager and its golden record will still be drifting through the galaxy, carrying the echoes of a civilization that once looked up at the stars and dared to reach for them. On August 20th, 1977, Voyager 2 lifted off from Cape Canaveral, Florida, atop a Titan IIIe Centaur rocket. 16 days later, on September 5th, 1977, Voyager 1 followed on a separate Titan IIIe Centaur. Despite launching second, Voyager 1 was placed on a faster trajectory that would bring it to Jupiter first, hence the numbering. Both launches were tense affairs, as any rocket launch is. There is always the possibility of failure, of explosion, of malfunction, of all those years of work and all those billions of miles of possibility being destroyed in a fireball of propellant and debris. But both launches were successful. Both Voyagers cleared Earth's atmosphere, separated from their rockets, deployed their instruments, and set course for Jupiter. The Grand Tour, or what remained of it after the budget cuts and redesigns, had begun. Humanity's most distant journey was underway. If you are finding this story as incredible as I think you should be, if the idea of a machine built with 1970s technology still functioning 15 billion miles from Earth gives you chills, then I want you to do something for me right now. Hit that subscribe button. Tap the bell icon so you get notified when we release our next deep dive. And drop a comment below this video telling me, if Voyager's golden record is found 1,000,000 years from now by an alien civilization, what do you think they would think of us? What would they learn about humanity from the sounds of our world, the music of our cultures, the voices of our children? I genuinely want to know what you think, so leave your answer in the comments. And share this video with someone who loves space, someone who gets excited about the big questions, someone who looks up at the night sky and wonders what is out there. Because the story we are about to tell, the story of what Voyager found at the edge, is a story that every human being on this planet deserves to hear. Now, let us follow Voyager into the outer solar system and witness the discoveries that changed everything we knew about our planetary neighborhood. Voyager 1 reached Jupiter in March of 1979, followed by Voyager 2 in July of the same year. What they found there revolutionized our understanding of the largest planet in our solar system and its extraordinary collection of moons. Jupiter, as seen through Voyager's cameras, was a world of stunning beauty and terrifying power. The Great Red Spot, which astronomers had observed through telescopes for over 300 years, was revealed in breathtaking detail as a colossal anticyclonic storm, large enough to swallow 2 or 3 Earths whole. The swirling bands of clouds, in shades of orange, white, brown, and red, were resolved into intricate patterns of turbulence, vortices, and atmospheric dynamics that no Earth-based telescope had ever captured. The atmosphere was a roiling, violent, magnificent spectacle of fluid dynamics on a scale that dwarfed anything on our own planet. But it was Jupiter's moons that produced the most shocking discoveries. Jupiter has a large family of natural satellites, but 4 of them, the so-called Galilean moons, are worlds in their own right, each one a fascinating and unique place. And Voyager revealed them to us for the very first time. Io, the innermost of the Galilean moons, was the source of arguably the single most unexpected discovery of the entire Voyager mission. As Voyager 1 approached Io, navigation engineer Linda Morabito noticed something extraordinary in one of the images. There, on the limb of Io, silhouetted against the black of space, was a plume, a volcanic plume, an active eruption, hurling material hundreds of kilometers above the moon's surface. Io had active volcanoes. This was absolutely staggering. Before Voyager, the only body in the solar system known to have active volcanism was Earth. The prevailing assumption was that small cold bodies like Jupiter's moons would be geologically dead, their interiors long since cooled and solidified. But Io was not dead. Io was the most volcanically active body in the entire solar system, more active than Earth by a significant margin, its surface constantly being resurfaced by eruptions of sulfur and silicate lava, driven by the intense tidal heating generated by Jupiter's enormous gravitational pull. Voyager found at least 9 active volcanic eruptions during its flyby. 9 on a single moon. The textbooks had to be rewritten overnight. Europa, the next moon out, presented a completely different but equally astonishing picture. Voyager's cameras revealed a surface unlike anything seen before in the solar system. A vast, smooth, icy plain, crisscrossed by an intricate network of dark lines and ridges. Europa's surface was remarkably flat, with almost no craters, which meant it was geologically young, constantly being renewed. The dark lines looked like cracks in an ice sheet, and the implication was tantalizing. Beneath Europa's icy crust, there might be a vast ocean of liquid water, kept warm by the same tidal heating that drove Io's volcanoes. Liquid water. Beneath the surface of a moon of Jupiter. If this was true, and subsequent missions would provide increasingly compelling evidence that it was, then Europa became one of the most important targets in the search for extraterrestrial life in our solar system. The discovery of Europa's cracked ice surface by Voyager was the moment when the idea of life beyond Earth went from pure science fiction to genuine scientific possibility. Ganymede, the largest moon in the solar system, bigger even than the planet Mercury, revealed a surface divided into 2 distinct terrain types: ancient, dark, heavily cratered regions, and younger, lighter, grooved terrain that suggested past geological activity. Callisto, the outermost Galilean moon, was the opposite of Io, a heavily cratered ancient surface that appeared to have been geologically inactive for billions of years, its face a record of impacts stretching back to the earliest days of the solar system. Voyager also discovered that Jupiter had a faint ring system, something that had never been detected from Earth. The rings were thin, dark, and composed of tiny dust particles, completely different from Saturn's magnificent rings, but significant in their own right. Beyond these headline discoveries, Voyager revealed Jupiter's intense radiation environment, magnetic field, and magnetosphere in unprecedented detail. Jupiter's magnetic field is the strongest of any planet in the solar system, about 20,000 times stronger than Earth's, and its magnetosphere, the region of space dominated by that magnetic field, extends for millions of miles, creating a lethal radiation zone that nearly fried Voyager's electronics during the flyby. The spacecraft received a radiation dose equivalent to about 1,000 times the lethal dose for a human being. The fact that Voyager survived this onslaught and continued to function is a testament to its robust design and a fair measure of good fortune. After Jupiter, Voyager 1 and Voyager 2 continued on to Saturn, arriving in November 1980 and August 1981, respectively. And if Jupiter had been a revelation, Saturn was a work of art. There is simply no other way to describe what Voyager found at the ringed planet. Saturn's rings, which through Earth-based telescopes appeared as a few broad, smooth bands, were revealed by Voyager to be an astonishingly complex system of thousands upon thousands of individual ringlets, gaps, waves, kinks, braids, and structures of breathtaking intricacy. The rings were composed of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders, all orbiting Saturn in an impossibly thin, flat disk that extended for hundreds of thousands of kilometers but was only a few tens of meters thick in many places. The thinness of the rings relative to their extent was mind-boggling, proportionally thinner than a sheet of paper stretched across a football field. Voyager discovered several phenomena in Saturn's rings that defied immediate explanation. Among the most mysterious were the so-called spokes, dark, radial features that appeared and disappeared in the B ring, seeming to float above the ring plane and rotate with the planet rather than with the orbital speed of the ring particles, which should be different at different distances from Saturn. These spokes violated the simple rules of orbital mechanics and were eventually attributed to interactions between tiny, electrically charged ring particles and Saturn's magnetic field, but they remained a source of fascination and debate for decades. Voyager also discovered that Saturn's rings were maintained and shaped by the gravitational influence of small moons, called shepherd moons, which orbited within and near the rings and acted as gravitational sculptors, herding ring particles into narrow ringlets and sharp edges. The F ring, a narrow, twisted ring discovered by Pioneer 11 just before Voyager's arrival, was found to be bounded by two small shepherd moons, Prometheus and Pandora, whose gravitational influence created an intricate, braided structure that looked almost organic in its complexity. But perhaps the most consequential decision of the entire Voyager mission was made at Saturn. The decision to redirect Voyager 1 for a close flyby of Titan. Titan, Saturn's largest moon, had been a source of fascination for decades because it was the only moon in the solar system known to possess a significant atmosphere. Earth-based observations had detected methane in Titan's atmosphere, and there were hints that the atmosphere might be thick, possibly even denser than Earth's. The scientific community was desperate to learn more, and so NASA made the call. Voyager 1 would be aimed at Titan, passing within about 4,000 kilometers of the moon's surface. This trajectory would give Voyager 1 an incredible close look at Titan's atmosphere, but it came with a cost. The gravity assist from the Titan flyby would deflect Voyager 1 sharply upward, out of the plane of the solar system, making it impossible for the spacecraft to continue on to Uranus and Neptune. Voyager 1's grand tour of the planets was over. It would see no more worlds. What Voyager 1 found at Titan was both amazing and frustrating. Titan's atmosphere was indeed thick, far thicker than anyone had expected. The surface pressure was about 1.5 times that of Earth, and the atmosphere extended hundreds of kilometers above the surface, far higher than Earth's atmosphere relative to the planet's size. The atmosphere was primarily nitrogen, just like Earth's, with significant amounts of methane and other organic compounds. But the atmosphere was also completely opaque. A thick, orange-brown haze of organic aerosols shrouded the entire moon, making it impossible for Voyager's cameras to see the surface. Titan remained, visually at least, a mystery, its surface hidden beneath an impenetrable veil. It would take another 25 years, until the arrival of the Cassini-Huygens mission in 2004 and the descent of the Huygens probe through Titan's atmosphere in 2005, before humanity finally saw what lay beneath those clouds. a world of liquid methane lakes, icy mountains, and vast dune fields, an alien landscape that was, in some ways, eerily reminiscent of Earth. With Voyager 1 now heading out of the solar system, the burden of continuing the grand tour fell entirely on Voyager 2, and Voyager 2 rose to the challenge magnificently. After its Saturn encounter, Voyager 2 was aimed at Uranus, reaching the ice giant in January 1986. Uranus was, in many ways, the strangest planet Voyager visited. It was a world tipped on its side, with an axial tilt of 98 degrees, meaning that it essentially rolls around the sun like a ball. The cause of this extreme tilt is thought to be a massive collision with an Earth-sized object early in the solar system's history, an impact so violent that it knocked the entire planet sideways. Voyager 2 revealed a planet that appeared deceptively bland at first glance, its atmosphere a nearly featureless blue-green sphere, quite different from the turbulent, banded atmospheres of Jupiter and Saturn. But beneath this calm exterior, Uranus harbored secrets. Its magnetic field was wildly off-center and tilted at 60 degrees to its rotation axis, a configuration so unusual that it suggested Uranus's interior structure was fundamentally different from what scientists had assumed. Voyager discovered 10 new moons and 2 new rings at Uranus, bringing the known ring count to 11. And then there was Miranda. Miranda, the innermost of Uranus's 5 major moons, was the surprise star of the Uranus encounter. This small moon, only about 470 kilometers in diameter, displayed a surface of extraordinary geological complexity. There were huge, angular features called coronae, fault canyons up to 20 kilometers deep, which is about 12 times deeper than the Grand Canyon relative to the moon's size, and bizarre patchwork terrain that looked as if the moon had been shattered into pieces and then clumsily reassembled. One popular hypothesis suggested that Miranda had indeed been disrupted by a massive impact, and had reaccreted from the fragments, producing its chaotic, mismatched surface. Later analysis suggested that the features might instead be the result of internal geological processes driven by tidal heating. But either way, Miranda's tortured face was one of the most visually stunning and scientifically perplexing surfaces in the solar system. 3 years later, in August 1989, Voyager 2 reached Neptune, the farthest planet from the Sun, and the last stop on its grand tour. Neptune was a glorious, deep blue world, far more visually dynamic than the bland face of Uranus. Voyager 2 discovered the Great Dark Spot, a massive storm system in Neptune's atmosphere, comparable in size to the Great Red Spot on Jupiter, though Neptune is a much smaller planet. The spacecraft measured the fastest winds ever recorded on any planet, exceeding 2,000 kilometers per hour, an astonishing feat for a world so far from the Sun that it receives less than 1,000th of the sunlight that Earth receives. Where does the energy come from to drive such extreme weather? Neptune radiates more than twice as much energy as it receives from the Sun, suggesting a powerful internal heat source, but the exact mechanism remains a subject of scientific investigation. And then there was Triton, Neptune's largest moon, and the final solid world that Voyager would ever visit. Triton was a revelation. It was clearly a captured object, not formed in place around Neptune but snatched from the Kuiper Belt, as evidenced by its retrograde orbit, meaning it orbits Neptune in the opposite direction to the planet's rotation. Triton's surface was young, sparsely cratered, and geologically active, which was shocking for a body so small and so far from the Sun. Most spectacularly, Voyager discovered active geysers on Triton, plumes of nitrogen gas erupting from beneath the moon's surface and reaching up to 8 kilometers into the thin atmosphere before being swept downwind. active geological processes on a tiny, frozen moon 4.5 billion kilometers from the Sun. Triton, like Europa and Io before it, demonstrated that the solar system was far more dynamic, far more alive, far more surprising than anyone had imagined before Voyager. After Neptune, there were no more planets to visit. Voyager 2's grand tour, the most productive journey of exploration in human history, was complete. Both Voyagers had performed beyond anyone's wildest expectations, transforming 4 distant, mysterious giant planets and their families of moons from abstract dots of light into real, vivid, understood worlds. The data they returned would keep scientists busy for decades, filling thousands of scientific papers and fundamentally reshaping our understanding of the solar system. But there was one more act in the planetary phase of Voyager's story, and it was not a scientific observation in the traditional sense. It was, instead, one of the most emotionally powerful moments in the history of space exploration. On February 14, 1990, Valentine's Day, with both Voyagers now heading away from the Sun and out of the planetary region of the solar system, Carl Sagan made a request to NASA. He asked them to turn Voyager 1's camera around, to point it back toward the inner solar system, and to take one final photograph. Not of a planet or a moon, but of home, of Earth. From a distance of approximately 6 billion kilometers, 3.7 billion miles, Voyager 1 captured an image that would become one of the most famous and most important photographs ever taken. In that image, Earth appears as a tiny, faint, blue-white speck, less than a single pixel in size, suspended in a scattered ray of sunlight. A mote of dust caught in a sunbeam. That image became known as the pale blue dot, and it inspired one of the most profound and beautiful passages in all of scientific literature. Carl Sagan wrote and later spoke aloud in a recording that has been heard by millions of people around the world. Look again at that dot, that's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering. Thousands of confident religions, ideologies and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. That image and those words changed something in the collective consciousness of our species. They gave us a perspective that is almost impossible to achieve by any other means, a view of ourselves from the outside, from a distance so vast that all of our conflicts, all of our divisions, all of our petty struggles become invisible, dissolved into the overwhelmingly obvious truth that we are all, every single one of us, passengers on the same tiny, fragile, beautiful world, alone in the immensity of space. After the pale blue dot image was taken, Voyager 1's cameras were turned off permanently. There would be no more pictures. The spacecraft no longer needed eyes. What it needed now were ears, and instruments that could feel and measure the invisible environment around it. Because Voyager was heading somewhere no camera could usefully photograph, somewhere no human mind had ever directly sensed. It was heading toward the edge. Now, here's where our story takes a turn from triumph and wonder toward something more unsettling. Because to understand what Voyager found at the edge of the solar system, you first need to understand what the edge of the solar system actually is. And the answer is not what most people think. When most people hear the phrase, the edge of the solar system, they think of the outermost planet, they think of Neptune, or they think of Pluto, if they still consider it a planet. They imagine a neat boundary, a line drawn in space, beyond which our solar system ends and interstellar space begins. But the reality is far more complex, far more dynamic, and far more interesting than that. The true boundary of the solar system is not defined by planets. It is defined by the Sun. Specifically, it is defined by the Sun's solar wind and magnetic field, and the immense, invisible bubble they create around our entire star system. Here is how it works. The Sun is not just a ball of light and heat sitting passively in the center of the solar system. It is an active, dynamic, violent star that is constantly releasing a torrent of energy and matter into space. One of the most significant outputs of the Sun is the solar wind, a continuous stream of charged particles, mostly protons and electrons, that flows outward from the Sun's corona at speeds ranging from 300 to 800 kilometers per second. That is roughly 1,000,000 miles per hour. This is not a gentle breeze. This is a supersonic torrent of plasma, screaming outward from the Sun in all directions, filling the entire solar system with charged particles and magnetic field lines. As this solar wind flows outward, it creates a vast bubble in space, a region where the Sun's particles and magnetic field dominate the environment. This bubble is called the heliosphere, from the Greek word helios, meaning sun. The heliosphere is not a solid shell or a fixed structure. It is a dynamic, breathing, fluctuating bubble of solar influence, and everything inside it, every planet, every moon, every asteroid, every comet, every speck of dust, and every living thing on Earth exists within this bubble. The heliosphere is, in a very real sense, our home within the galaxy. It is the Sun's sphere of influence, the region where our star holds sway. But the solar wind does not continue outward forever. Eventually, at enormous distances from the Sun, the solar wind runs into something. It encounters the interstellar medium, the thin gas, dust, and magnetic fields that fill the space between stars in our galaxy. The interstellar medium is not empty. It is not nothing. It has its own density, its own temperature, its own magnetic field, and its own pressure. And at some point, the outward pressure of the Sun's solar wind becomes equal to the inward pressure of the interstellar medium, and the solar wind is forced to stop. This is the boundary. This is the edge. This is where the Sun's domain ends and the galaxy's domain begins. And it is not a simple, clean, static line. It is a complex, layered, turbulent, and constantly shifting transition zone that extends across billions of miles. Let me take you through the layers of this boundary, because understanding them is critical to understanding what Voyager found and why it matters. The first layer is called the termination shock. Imagine the solar wind as a river flowing outward from the Sun at supersonic speed. Now, imagine that river hitting a wall, an obstacle that forces it to slow down abruptly. That is what happens at the termination shock. The solar wind, which has been flowing supersonically, meaning faster than the speed at which pressure waves can travel through it, suddenly encounters enough resistance from the interstellar medium that it decelerates to subsonic speeds. This is an actual shock wave, similar in concept to the sonic boom created by an airplane breaking the sound barrier, but in reverse. The solar wind breaks through the sound barrier in the other direction, going from supersonic to subsonic. This transition is sudden, violent, and accompanied by a dramatic increase in the temperature, density, and turbulence of the solar wind plasma. Voyager 1 crossed the termination shock in December 2004, at a distance of about 94 astronomical units from the Sun, where 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. Voyager 2 crossed the termination shock in August 2007, at a distance of about 84 astronomical units. The fact that these two crossings occurred at significantly different distances was itself a revelation, because it told scientists that the termination shock is not a perfect sphere centered on the Sun. It is asymmetric, pushed closer to the Sun in some directions and farther out in others, shaped by the pressure and magnetic field of the interstellar medium. Beyond the termination shock lies the heliosheath, the second layer of the boundary. The heliosheath is the region where the solar wind, now slowed to subsonic speeds, piles up and becomes hot, turbulent, and chaotic. Think of it like the splash zone beyond a waterfall. The water has hit the rocks and is now swirling, churning, foaming, and flowing in unpredictable patterns. The heliosheath is the solar wind's equivalent of that splash zone, a thick, hot, turbulent region of compressed solar plasma that extends for billions of miles. Both Voyagers spent years crossing the heliosheath, and the data they returned from this region was some of the most surprising and confusing of the entire mission. The magnetic field in the heliosheath was far more disordered than expected. The plasma flow was chaotic and variable, and the region was filled with unexpected structures and phenomena that no model had predicted. Beyond the heliosheath lies the heliopause, the actual outer boundary of the heliosphere, the point where the Sun's solar wind finally stops completely, balanced by the equal and opposite pressure of the interstellar medium. This is the skin of the bubble. This is the membrane that separates us from the galaxy. This is the edge. And this is what Voyager crossed. Voyager 1 crossed the heliopause on August 25, 2012. It was a date that will be recorded in the history books alongside the great milestones of human exploration, alongside the first circumnavigation of the globe, the first ascent of Everest, the first human in space, the first steps on the moon. On that date, Voyager 1 became the first human-made object in history to enter interstellar space. It had left the Sun's domain. It was now in the territory of the galaxy, in the vast, cold, dark spaces between the stars. And the data it sent back from that crossing, and from the interstellar medium beyond, is what has scientists so deeply concerned. But before we get into the specifics of what Voyager found, I need to pause and emphasize something that many people do not fully appreciate. The heliopause is not just a line on a chart. It is not just a boundary of scientific interest. The heliosphere, the bubble enclosed by the heliopause, is our shield. It is our protection. It is the invisible cosmic force field that has been protecting every living thing on Earth for billions of years. The heliosphere deflects a significant fraction of the galactic cosmic rays that would otherwise bombard the inner solar system. Galactic cosmic rays are high-energy particles, mostly protons and atomic nuclei, that are produced by the most violent events in the galaxy. Supernova explosions, the jets of black holes, the shock waves of colliding galaxies. These particles travel at close to the speed of light and carry enormous energies. When they strike biological tissue, they can damage DNA, cause mutations, trigger cancer, and destroy cells. When they strike Earth's atmosphere, they produce cascades of secondary particles that reach the surface. At the levels we currently experience on Earth, galactic cosmic rays are a manageable background radiation, one contributing factor among many to the natural mutation rate that drives evolution. But if the flux of galactic cosmic rays were to increase significantly, the consequences could be severe. Increased cancer rates, damage to ecosystems, depletion of the ozone layer, and potentially even effects on cloud formation and climate. The heliosphere is what stands between us and a much higher flux of these deadly particles. And it is the health, the size, the shape, and the integrity of this shield that Voyager's data has called into question. Let us now return to August 25, 2012, and examine what actually happened when Voyager 1 crossed the heliopause. The crossing was not what scientists expected. For years, theorists had debated what the transition from the heliosphere to interstellar space would look like. Most models predicted a relatively clean boundary, a region where the solar wind plasma would drop off sharply. The interstellar plasma would take over, the magnetic field would change direction, and the cosmic ray intensity would spike. And some of these predictions were correct, but the reality was messier, more confusing, and more disturbing than any model had predicted. The first sign that Voyager 1 was approaching the heliopause came in mid-2012, when the spacecraft entered a strange and unexpected region that scientists would later call the magnetic highway, or the heliospheric depletion region. In this region, something bizarre happened. The intensity of solar energetic particles, the lower energy-charged particles produced by the Sun, dropped precipitously, falling to near zero. Simultaneously, the intensity of galactic cosmic rays, the high-energy particles from outside the solar system, spiked dramatically. This is exactly what you would expect to see at the edge of the heliosphere. But here is the puzzling part. The magnetic field direction did not change. The magnetic field in this region was still aligned with the Sun's magnetic field, not with the interstellar magnetic field. By all rights, if Voyager 1 had truly crossed into interstellar space, the magnetic field should have changed direction. But it hadn't. So, where was Voyager? Inside the heliosphere or outside? It seemed to be in some kind of intermediate zone, a region that was partially connected to both the heliosphere and the interstellar medium, allowing particles to flow in and out along magnetic field lines like cars on a highway. This was the magnetic highway, and it was not predicted by any theoretical model. Its existence suggested that the boundary of the heliosphere was far more complex than a simple bubble wall. It was layered, structured, porous, and connected to the outside in ways that no one had anticipated. Eventually, on August 25, 2012, the plasma data confirmed that Voyager 1 had indeed crossed the heliopause. The density of the surrounding plasma jumped dramatically, from the low density characteristic of the solar wind to the much higher density characteristic of the interstellar medium. This was the definitive signature. Voyager 1 was in interstellar space, but even this confirmation came with caveats and confusions. The magnetic field direction changed only slightly, not as dramatically as many models had predicted. The transition was sharp in terms of plasma density, but gradual in terms of magnetic field orientation. The boundary was not a clean wall. It was a complex, multi-layered transition zone that defied simple categorization. 6 years later, on November 5, 2018, Voyager 2 crossed the heliopause at a different location, providing the invaluable second data point that scientists needed to begin understanding the three-dimensional structure of the boundary. And Voyager 2 had a crucial advantage over Voyager 1. Its plasma science experiment, or PLS instrument, was still functioning. Voyager 1's PLS had stopped working way back in 1980, which meant that all of Voyager 1's plasma measurements near the heliopause had to be inferred indirectly from other instruments. Voyager 2, with its working PLS, could directly measure the plasma environment as it crossed the boundary. And what it measured was striking. The crossing was remarkably sharp. The plasma density jumped by a factor of about 20 within a very short distance, like crossing through a wall. The solar wind plasma essentially vanished and was replaced, almost instantaneously, by interstellar plasma. It was as if Voyager 2 had passed through a membrane, a skin, a barrier of remarkable thinness and definition. But the two crossings were not identical. Voyager 1 crossed at a higher latitude and a greater distance from the Sun, while Voyager 2 crossed at a lower latitude and a shorter distance. The fact that the heliopause was at different distances in different directions confirmed what the termination shock crossings had already suggested. The heliosphere is not a perfect sphere. It is distorted, compressed on one side by the interstellar medium and perhaps elongated on the other. And the nature of the crossings themselves was different. Voyager 1's crossing involved the mysterious magnetic highway region, while Voyager 2's crossing was cleaner and more abrupt. The boundary of the heliosphere, it seemed, was different in different places, with different structures, different layering, and different properties depending on the direction. And now we come to the heart of the matter. Now we come to the data that has confirmed what scientists feared. Let me lay it out for you, piece by piece, because each piece is significant, and together they paint a picture that is profoundly unsettling. The first thing Voyager found is what scientists have been calling the hydrogen wall. As Voyager approached and crossed the heliopause, it detected a region of enhanced density in neutral hydrogen atoms, a piling up of interstellar hydrogen at the boundary of the heliosphere. Imagine the heliosphere as a boat moving through water. As the boat pushes forward, water piles up at the bow, creating a wave. Similarly, as the heliosphere moves through the interstellar medium, neutral hydrogen atoms pile up at the leading edge, compressed between the outward-pushing solar wind and the incoming interstellar material. This hydrogen wall had been theoretically predicted, and there were tentative detections from the Hubble Space Telescope as early as the mid-1990s. But Voyager's in-situ measurements confirmed its existence and revealed that it was denser than many models had predicted. The interstellar medium is not just passively sitting outside our heliosphere. It is actively pressing against it, piling up against the boundary, and exerting a force that our solar wind must constantly fight against. The second thing Voyager found is that galactic cosmic ray intensities beyond the heliopause are significantly higher than expected. Inside the heliosphere, the solar wind and the Sun's magnetic field act to deflect and slow incoming galactic cosmic rays, a process known as solar modulation. The strength of this modulation varies with the 11-year solar cycle. During solar maximum, when the Sun is most active and the solar wind is strongest, more cosmic rays are deflected, and fewer reach the inner solar system. During solar minimum, the modulation weakens, and more cosmic rays penetrate inward. Scientists have long known this basic framework, but Voyager's data from beyond the heliopause provided the first direct measurements of the unmodulated galactic cosmic ray flux, the true baseline intensity of cosmic rays in our local interstellar neighborhood, before the heliosphere has had any chance to filter them. And the numbers were sobering. The cosmic ray intensity outside the heliosphere was higher in certain energy ranges than the most pessimistic models had estimated. This means that the total amount of galactic cosmic radiation pressing against our shield is greater than we thought. The enemy, so to speak, is stronger than we assumed. The third thing Voyager found is that the heliosphere appears to be more porous than expected. The magnetic highway region discovered by Voyager 1 before its heliopause crossing was a clear demonstration of this. In that region, galactic cosmic rays were streaming into the heliosphere, and solar particles were streaming out along magnetic field lines that connected the inside and outside of the boundary. The heliosphere was not a sealed container. It had leaks. It had channels and connections that allowed particles to pass through the boundary in both directions. This means that even inside the heliosphere, the shielding against galactic cosmic rays may not be as complete as previously modeled. There are places, there are times, there are configurations of the magnetic field that allow cosmic rays to penetrate deeper into the heliosphere than they should, reaching closer to Earth than our models predicted. The fourth thing Voyager found, and this is perhaps the most far-reaching discovery of all, is that the shape of the heliosphere is not what we thought. For decades, the standard textbook illustration of the heliosphere showed a comet-like shape. A blunt, rounded nose at the front, where the heliosphere pushes into the interstellar medium, and a long, trailing tail stretching behind, like the tail of a comet or the wake of a boat. This shape was a natural consequence of the sun's motion through the interstellar medium. Just as a boat moving through water creates a bow wave and a wake, the sun's motion through the interstellar medium was expected to compress the heliosphere at the front and stretch it at the back, creating a long heliotail. But Voyager's data, combined with observations from the IBEX spacecraft, which orbits Earth and maps the heliosphere's boundary by detecting energetic neutral atoms, and with sophisticated computer simulations, has challenged this picture dramatically. Some models now suggest that the heliosphere has no long tail at all. Instead, it may be roughly spherical, or even shaped like a croissant, a deflated rounded blob with two lobes and a pinched middle. The debate is ongoing and intense. Different research groups, using different models and different interpretations of the data, have reached very different conclusions about the heliosphere's shape. But one thing is increasingly clear. The simple comet tail model is probably wrong. And the shape matters enormously because the shape determines which parts of the solar system are exposed to interstellar cosmic rays from which directions. A long tail would mean that the rear of the heliosphere provides significant shielding against cosmic rays approaching from behind. No tail, or a short, deflated tail, means that cosmic rays can approach from virtually any direction, and the shielding is more limited than the comet tail model would suggest. The fifth thing Voyager found, and this has been confirmed by continued measurements over the years since both spacecraft crossed into interstellar space, is that the interstellar medium itself is not the quiet, static, uniform void that many people imagine. It is an active, dynamic, structured environment with its own weather, its own turbulence, and its own variability. Voyager 1 has detected a persistent, low-level hum of plasma oscillations in the interstellar medium, a faint but constant vibration in the density of the interstellar plasma. This hum is not dramatic, but it is always there, and it tells us that the interstellar medium is constantly in motion, constantly fluctuating, constantly alive with subtle waves and disturbances. In addition to this background hum, both Voyagers have detected occasional bursts of plasma activity, spikes in the plasma density associated with shock waves propagating through the interstellar medium. Shock waves that originated from energetic events on the Sun, coronal mass ejections that punched through the heliopause and sent ripples propagating into interstellar space. These observations reveal that the boundary between the heliosphere and the interstellar medium is not a static wall but a dynamic interface, constantly being buffeted from both sides, constantly changing, constantly alive. And perhaps, most significantly, Voyager's measurements show that the density of the interstellar plasma has been gradually increasing as the spacecraft moves farther from the heliopause into the interstellar medium. This is important because it tells us something about the large-scale structure of the local interstellar environment. If the density is increasing with distance from the heliosphere, it suggests that the region immediately surrounding the heliosphere may be a local minimum in density, and that denser material lies further out. This is consistent with what we know about the local interstellar cloud, the warm, partially ionized cloud of gas and dust through which our solar system is currently traveling. The local interstellar cloud is about 30 light-years across, and recent research suggests that we may be near its edge, approaching a transition to a different interstellar environment. What that different environment looks like, whether it is denser or less dense, hotter or cooler, more or less magnetized, we do not yet know for certain. But there are indications from both Voyager's data and from astronomical observations of the surrounding interstellar medium that what lies beyond the local interstellar cloud may be denser, and if it is, the consequences for our heliosphere could be significant. Now, let me pull all of these findings together and explain why scientists are so concerned. Because each of these individual discoveries is important on its own, but it is the combined picture that is truly alarming. What Voyager has revealed is a heliosphere that is smaller than some models predicted, asymmetric in shape, more porous to cosmic rays than expected, bounded by a denser and more energetic interstellar medium than assumed, and far more variable and dynamic than the stable, static shield we once imagined. Our cosmic bubble of protection is thinner, leakier, more compressed, and more vulnerable than we thought. And the forces pressing against it from outside are stronger and more relentless than we assumed. This is what scientists feared, and this is what Voyager has now confirmed. Let me be very clear about what this means and why it matters, because the implications extend far beyond abstract astrophysics. They touch on the safety of life on Earth, the feasibility of human space exploration, and our understanding of the habitability of planets throughout the galaxy. Let us start with the most immediate and, for many people, the most personal concern: the safety of life on Earth. The heliosphere is our primary shield against galactic cosmic rays. If that shield is weaker or more variable than we thought, then Earth's exposure to cosmic radiation may be higher or more variable than our models have accounted for. Now, it is important to emphasize that this does not mean there is an immediate crisis. The heliosphere is still there, still functioning, still deflecting the majority of incoming galactic cosmic rays. The current level of cosmic radiation on Earth's surface is well within the range that life has adapted to over billions of years. We are not in immediate danger, but the concern is not about right now. The concern is about variability, about long-term trends, and about what happens when conditions change. And the evidence suggests that conditions have changed in the past, and will change again in the future. Here is why. Our solar system is not stationary. The Sun, along with all of its planets, moons, asteroids, and comets, is moving through the Milky Way galaxy at a speed of about 230 kilometers per second, completing one orbit around the galactic center every 225 to 250 million years. As it moves, it passes through different regions of the galaxy with different properties, different densities, different temperatures, different magnetic fields. Right now, as I mentioned, we are inside the local interstellar cloud, a warm, relatively low-density region of interstellar gas. But we will not always be here. Over time, the Sun will move into different interstellar environments, and those environments will interact with the heliosphere in different ways. If the Sun moves into a region of higher density interstellar material, the external pressure on the heliosphere will increase, compressing it, making it smaller. A smaller heliosphere means that the boundary, the heliopause, moves closer to the Sun, closer to the planets, closer to Earth. And a closer heliopause means less distance for the solar wind's magnetic field to deflect incoming cosmic rays, which means more cosmic rays reach the inner solar system, which means more cosmic radiation on Earth. This is not speculation. There is now compelling evidence that this has happened in the past. A landmark study published in Nature Astronomy in 2024 presented evidence that approximately 2 million years ago, the solar system encountered a dense cloud of interstellar material that compressed the heliosphere so dramatically that its boundary was pushed inside the orbit of Earth. Let me repeat that, because it is an extraordinary claim supported by increasingly robust evidence. 2 million years ago, the heliosphere may have been compressed so much that Earth was effectively outside the heliosphere, directly exposed to the unshielded interstellar medium and the full intensity of galactic cosmic rays. The evidence for this comes from multiple independent lines of investigation, including the detection of elevated concentrations of the radioactive isotopes iron-60 and plutonium-244 in deep-sea sediments and Antarctic snow dating to approximately 2 to 3 million years ago. These isotopes are not produced on Earth or in the solar system. They are produced in supernova explosions and are carried through space in the interstellar medium. Their presence in Earth's geological record at elevated concentrations suggests that interstellar material was reaching Earth's surface at higher than normal rates during that period. Exactly what you would expect if the heliosphere was compressed and Earth was more exposed to the interstellar environment. The timing of this event coincides roughly with significant events in Earth's geological and biological history, including the onset of the Pleistocene ice ages and changes in the African landscape that are thought to have influenced human evolution. I want to be cautious here because the causal links between heliosphere compression, cosmic ray exposure, and specific geological or biological events are still being researched and debated. Correlation is not causation, and the Earth system is complex enough that many factors contribute to climate change and evolutionary pressures. But the possibility, the tantalizing and frightening possibility, is that changes in the heliosphere driven by variations in the interstellar environment could have direct, measurable effects on Earth's climate and biosphere. The idea that the galaxy can reach down and touch the Earth, that interstellar conditions can influence the evolution of life on our planet, is one of the most profound and humbling ideas in all of science. And Voyager's data, by confirming the nature and properties of the heliosphere interstellar boundary, has made this idea far more concrete and far more credible. Now, let me take you to the second major implication: the feasibility of human space exploration, particularly missions beyond the inner solar system. For decades, space agencies around the world have been planning and dreaming of missions that would take humans beyond the Moon, to Mars, to the asteroid belt, and perhaps, someday, to the outer planets and beyond. But one of the most significant obstacles to deep space travel is radiation, specifically galactic cosmic rays. Inside the heliosphere, especially in the inner solar system where Earth orbits, we benefit from double protection. The heliosphere itself deflects a portion of incoming cosmic rays, and Earth's magnetic field and atmosphere provide additional shielding for those of us on the surface. Astronauts in low Earth orbit, such as those on the International Space Station, are still partially shielded by Earth's magnetic field, though they receive significantly higher radiation doses than people on the ground. But astronauts traveling to Mars or beyond would leave the protection of Earth's magnetic field and would rely solely on the heliosphere's shielding, plus whatever physical shielding their spacecraft can provide. And Voyager's data has shown that the heliosphere's shielding is less effective than we hoped. The cosmic ray flux outside the heliosphere is higher than many models predicted, which means the baseline from which solar modulation subtracts is higher, which means the cosmic ray flux even inside the heliosphere, especially in the outer regions, is higher. For astronauts on a multi-year Mars mission, the cumulative radiation dose from galactic cosmic rays is a serious health concern, increasing the risk of cancer, cardiovascular disease, neurological damage, and other health problems. Current spacecraft shielding technology is not adequate to fully protect against galactic cosmic rays, because these particles are so energetic that they can penetrate through several inches of aluminum or other conventional shielding materials. In fact, some types of shielding can actually make the problem worse, because when a high-energy cosmic ray strikes a thick layer of dense material, It can produce a shower of secondary particles that are even more biologically damaging than the original cosmic ray. Voyager's data has sharpened our understanding of this threat, and has made it clear that any serious plan for deep space human exploration must address the cosmic ray problem head-on. This means developing new shielding technologies, perhaps using hydrogen-rich materials or water as radiation barriers, exploring the possibility of active electromagnetic shielding that could deflect charged particles away from the crew compartment, or designing missions with shorter transit times to reduce cumulative exposure. None of these solutions is easy, and all of them add weight, complexity, and cost to mission designs. But Voyager has made it clear that the cosmic ray problem cannot be ignored or wished away. The galaxy is not a gentle place, and leaving the protection of Earth means facing the full reality of that harshness. And if the radiation environment inside the heliosphere is challenging, the environment outside is orders of magnitude worse. Any future interstellar mission, any attempt to send humans or even robotic probes beyond the heliosphere to another star system would face an unshielded galactic cosmic ray flux that Voyager has now measured directly for the first time. The data is unambiguous. Once you leave the heliosphere, you are exposed to the full and unfiltered intensity of galactic cosmic radiation, with no natural shield and no easy technological solution. This does not make interstellar travel impossible, but it makes it enormously more difficult than it would be if the interstellar medium were the benign, empty void that some optimistic models had suggested. Voyager has given us the ground truth, the actual numbers, and those numbers are sobering. The third major implication of Voyager's findings extends far beyond our own solar system to the question of habitability throughout the galaxy. Every star in the Milky Way has its own version of a heliosphere, known generically as an astrosphere. The size, shape, and effectiveness of a star's astrosphere depend on the strength of its stellar wind, the properties of the surrounding interstellar medium, and the star's motion through the galaxy. A star with a weak stellar wind, or a star passing through a dense region of interstellar material, will have a small, compressed astrosphere that provides little protection against galactic cosmic rays. A star with a powerful stellar wind in a low-density interstellar environment will have a large, robust astrosphere. This has direct implications for the habitability of exoplanets. When we assess whether a planet in the habitable zone of another star could support life, we typically focus on factors like the planet's distance from its star, its atmosphere, its temperature, and the presence of liquid water. But Voyager's findings remind us that there is another critical factor: cosmic ray shielding. A planet could have perfect temperature, abundant water, a rich atmosphere, and all the chemical ingredients for life. But if its star's astrosphere is too small or too weak to shield it from galactic cosmic rays, the radiation environment on that planet's surface could be hostile to the development and survival of complex life. This is particularly relevant for planets orbiting red dwarf stars, which are the most common type of star in the galaxy and which are primary targets in the search for habitable exoplanets. Red dwarfs are smaller, cooler, and less luminous than our Sun, and their stellar winds are generally weaker. This means their astrospheres may be smaller and less protective than our heliosphere. Planets in the habitable zones of red dwarfs orbit very close to their stars, which helps with temperature regulation but does nothing to mitigate cosmic ray exposure if the astrosphere is too small to shield them. Voyager's data, by providing the first direct measurements of the interaction between a stellar wind and the interstellar medium, has given us a calibration point, a real-world benchmark against which to model the astrospheres of other stars and assess the cosmic ray environments of their planets. And the picture that emerges is one where cosmic ray shielding is a significant and often underappreciated factor in planetary habitability, one that could dramatically reduce the number of truly habitable worlds in our galaxy. Let me now bring us forward to the most recent years, to the latest data and developments in the Voyager story, because even as we speak, both Voyagers are still out there, still functioning, still sending data, still pushing the boundaries of what we know. But they are aging, they are dying, and every year, every month, every day that they continue to operate is a gift, a precious, irreplaceable gift that scientists treasure more than almost anything else in their professional lives. As of the most recent updates, Voyager 1 is approximately 165 astronomical units from the Sun, more than 15 billion miles in interstellar space, moving away at about 3.6 astronomical units per year. Voyager 2 is approximately 137 astronomical units from the Sun, about 12.5 billion miles, also in interstellar space, moving at about 3.1 astronomical units per year. Both spacecraft are still communicating with Earth through the Deep Space Network, though the signal strength decreases every year as the distance grows and the transmitter power remains the same. But the most pressing concern is power. The RTGs on both Voyagers are producing less power every year as the plutonium-238 continues its inexorable decay. When the spacecraft launched in 1977, each one had about 470 watts of electrical power available. Now, that figure is down to approximately 200 watts, and it continues to drop by about 4 watts per year. NASA has been managing this decline by selectively turning off instruments and heaters, prioritizing the systems that are most scientifically valuable and most essential for basic spacecraft operations. Instruments that were designed to study planets and moons, systems that have not been needed since the 1980s, have long since been powered down. Even instruments that are still scientifically valuable in the interstellar medium have had to be turned off to conserve power. Each decision to shut down an instrument is a miniature funeral, a permanent goodbye to a capability that will never return. In late 2023, Voyager 1 experienced a serious technical crisis that, for a time, threatened to end its mission entirely. The flight data system, the computer responsible for packaging scientific and engineering data for transmission to Earth, began sending garbled, repetitive data. Instead of meaningful telemetry, Earth was receiving a meaningless pattern of ones and zeros. For weeks, engineers at JPL worked frantically to diagnose the problem, a challenging task when the patient is over 15 billion miles away, and every command takes 22 hours to arrive. Eventually, they traced the issue to a single faulty memory chip in the flight data system. The chip had failed, corrupting the software that formatted the data for transmission. The solution was elegant and painstaking. The engineers wrote a software patch that redistributed the code from the faulty chip across other parts of the computer's memory, working around the damaged hardware. The patch was uploaded to Voyager 1 and, after an agonizing 44-hour round-trip wait, it worked. Voyager 1 resumed sending coherent data. The mission was saved, but the incident was a stark reminder of just how fragile and finite Voyager's remaining operational life is. Every component on board is nearly 50 years old, operating far beyond its design life, in an environment of extreme cold and radiation that was never fully anticipated. Any one of 1,000 things could fail at any time, and there would be no repair mission, no spare parts, no way to fix it. When Voyager finally falls silent, it will be forever. The current best estimates suggest that both Voyagers will have enough power to operate at least 1 or 2 science instruments until approximately the late 2020s or early 2030s. After that, there will not be enough power to run any instruments, and the spacecraft will go silent. They will still be out there, of course, still hurtling through interstellar space at tens of thousands of miles per hour, still carrying the golden record, still bearing humanity's message to the cosmos. But they will be silent messengers, their voices extinguished, their data streams ended, their last whisper to Earth fading into the background noise of the universe. While Voyager continues its slow fade, other missions are picking up pieces of the story and adding new dimensions to our understanding of the heliosphere and its interaction with the interstellar medium. One of the most important of these is the Interstellar Boundary Explorer, or IBEX, a small NASA spacecraft launched in 2008 into Earth orbit. Unlike Voyager, which takes direct measurements of the heliosphere's boundary by physically traveling there, IBEX studies the boundary from a distance by detecting energetic neutral atoms, or ENAs. Here's how it works. At the heliosphere's boundary, charged particles from the solar wind and the interstellar medium interact in complex ways. Some of these interactions produce neutral atoms, atoms that have gained or lost electrons in charge exchange collisions and are no longer affected by magnetic fields. These neutral atoms travel in straight lines from the boundary back toward the inner solar system, where IBEX can detect them and use them to create a map of conditions at the boundary, much like a doctor uses X-rays that have passed through a patient's body to create an image of their internal structures. And IBEX found something that no one expected. It discovered a narrow, bright ribbon of intense ENA emission stretching across the sky, arcing across the nose of the heliosphere. This ribbon was not predicted by any model, and its discovery was one of the most surprising results in heliophysics in decades. Subsequent analysis has linked the ribbon to the interstellar magnetic field pressing against the outside of the heliosphere. The ribbon appears to be a region where the interstellar magnetic field is perpendicular to the line of sight from the Sun, creating enhanced charge exchange and ENA production. The existence and structure of the IBEX ribbon provide crucial information about the direction and strength of the interstellar magnetic field, and about how it interacts with and shapes the heliosphere. And the picture it reveals is consistent with Voyager's findings. The interstellar magnetic field is significant. It is pressing against the heliosphere, and it is shaping the boundary in ways that were not fully appreciated before these observations. Building on IBEX's success, NASA developed a successor mission called the Interstellar Mapping and Acceleration Probe, or IMAP. This mission was designed to provide far higher resolution and sensitivity than IBEX, creating much more detailed maps of the heliosphere interstellar boundary and studying the processes that accelerate particles in the outer heliosphere. IMAP represents the next generation of our attempt to understand the bubble we live in and its data, combined with the ongoing transmissions from both Voyagers, is creating the most comprehensive picture we have ever had of the heliosphere and its environment. There is also New Horizons, the spacecraft that made the historic flyby of Pluto in 2015, and continued on to visit the Kuiper Belt object Arrokoth in 2019. New Horizons is now in the outer heliosphere, heading outward, but still well inside the heliopause. Its measurements of the solar wind at great distances from the Sun are providing valuable data on how the solar wind evolves and weakens as it expands outward, complementing Voyager's measurements from the other side of the boundary. Together, Voyager's interstellar measurements, IBEX and IMAP's remote sensing of the boundary, and New Horizons' outer heliosphere measurements are creating a three-dimensional, multi-perspective understanding of the heliosphere that was impossible just a decade ago. And what this combined picture reveals is both awe-inspiring and unsettling. The heliosphere is a dynamic, breathing, fluctuating entity, constantly responding to changes in the solar wind and in the interstellar environment. It swells during solar maximum and contracts during solar minimum. It is compressed on the side facing the interstellar wind, and may be rounder or more irregularly shaped than the classic comet tail model suggested. It is bounded by a complex, multi-layered transition zone that is more porous and more structured than expected, with magnetic connections that allow cosmic rays to penetrate and solar particles to escape. And it exists within an interstellar environment that is itself variable, structured, and potentially changing as the solar system moves through the galaxy. The scientific debate about the heliosphere's shape deserves a deeper exploration, because it gets to the heart of how well protected we are and from which directions threats might come. For decades, the dominant model was the comet tail model, also sometimes called the windsock model, in which the heliosphere has a blunt, rounded upstream side, where the solar wind meets the interstellar wind head-on, and a long, elongated downstream tail, stretched by the ram pressure of the interstellar medium flowing around the heliosphere like air flowing around a car. This model was intuitive, physically reasonable, and consistent with the limited data available at the time. But starting around 2015, a team of researchers led by Merav Ofer at Boston University proposed a radically different model based on new interpretations of Voyager and IBEX data, combined with sophisticated magnetohydrodynamic simulations. In Ofer's model, the heliosphere does not have a long, trailing tail at all. Instead, it is deflated, roughly spherical or slightly elongated, with two broad lobes separated by a pinch in the middle, shaped more like a croissant or a deflated beach ball than a comet. The key insight in Ofer's model is the role of the Sun's magnetic field, specifically the heliospheric current sheet, a vast, wavy surface that separates regions of opposite magnetic polarity in the heliosphere. In the traditional comet tail model, this current sheet was not given a dominant role in shaping the heliosphere's large-scale structure. In Ofer's model, the instabilities and dynamics of the current sheet play a central role, preventing the formation of a long, stable tail, and instead creating a shorter, more turbulent, more irregularly shaped structure. This debate is still very much active. Other groups have produced models that show intermediate shapes, or that support the traditional comet tail geometry under different assumptions about the interstellar magnetic field and the solar wind's properties. The truth is that we do not yet have enough data to definitively determine the heliosphere's shape. Voyager gives us measurements along only two lines of sight. IBEX and IMAP provide two-dimensional maps from Earth's perspective, and the models depend sensitively on input parameters that are still uncertain. But the fact that the shape is debated, and that leading researchers are arguing for a much smaller, more compact heliosphere than the traditional model, is itself significant. If the heliosphere is indeed more compact, it provides less shielding volume, and the direction-dependent protection against cosmic rays is different from what the comet tail model would predict. There is another related question that Voyager's data has illuminated. Does the heliosphere have a bow shock? In the comet tail model, as the heliosphere moves through the interstellar medium is expected to be deflected around the heliosphere, much like water flowing around a rock in a stream. If the heliosphere is moving through the interstellar medium faster than the speed of sound in that medium, a bow shock would form ahead of the heliosphere, an interstellar shock wave that heats and compresses the interstellar gas before it encounters the heliopause itself. This bow shock would be analogous to the sonic boom ahead of a supersonic airplane. For years, scientists assumed that the sun's motion through the local interstellar cloud was fast enough to create such a bow shock. But data from IBEX and revised measurements of the interstellar magnetic field strength suggested that the speed of sound in the local interstellar medium is higher than previously thought, which means the sun's motion may be subsonic relative to the interstellar medium. If the motion is subsonic, there is no bow shock, only a gentler bow wave that gradually deflects the interstellar material around the heliosphere without creating a sharp shock front. The current consensus leans toward no bow shock, or, at most, a very weak one. And this matters because a bow shock would provide an additional layer of defense, heating and deflecting incoming interstellar material before it reached the heliopause. Without a bow shock, the interstellar medium meets the heliosphere directly, with full force and no advanced disruption. Our defenses are one layer thinner than we once imagined. Let me now take you on a journey into the deeper implications, the ones that extend beyond our solar system and our current moment in time to the grand sweep of cosmic history and the future of life in the galaxy. Because Voyager's discoveries at the edge of the solar system do not exist in isolation. They are part of a much larger story, the story of how stars and their planetary systems interact with the galaxy that hosts them, and how that interaction shapes the conditions for life across cosmic time. Our Sun is one of hundreds of billions of stars in the Milky Way galaxy. It orbits the galactic center in a roughly circular path at a distance of about 26,000 light-years, taking approximately 225 to 250 million years to complete one orbit. This period is sometimes called a galactic year. In the 4.6 billion-year history of the solar system, the Sun has completed roughly 18 to 20 galactic orbits, each one carrying it through a different cross-section of the galaxy's structure. And the galaxy is not a uniform, homogeneous place. It has structure, spiral arms of higher density, rich in young stars, gas and dust, interarm regions of lower density, giant molecular clouds where new stars are being born, hot, rarefied bubbles carved out by supernova explosions, and vast stretches of relatively tenuous interstellar medium. As the Sun orbits the galaxy, it passes through all of these different environments, and each one interacts with the heliosphere differently. When the Sun passes through a region of high-density interstellar material, the external pressure on the heliosphere increases, compressing it. When it passes through a low-density region, the heliosphere can expand. When it passes near a recent supernova remnant, it may encounter a blast wave of hot, fast-moving gas that could dramatically reshape or compress the heliosphere. When it passes through a spiral arm, the density of the interstellar medium increases, and the cosmic ray flux may also increase because spiral arms are regions of active star formation and supernova activity. There have been multiple attempts to correlate the timing of the Sun's spiral arm crossings with major geological and biological events on Earth, including mass extinctions, ice ages, and changes in biodiversity. The evidence is intriguing but not conclusive. Some studies have found suggestive correlations between the timing of spiral arm crossings and periods of increased extinction rates or climate variability. Others have found no significant correlations. The difficulty is that the timing of the Sun's galactic orbit is not precisely known. The locations and shapes of the spiral arms in the past are uncertain, and the Earth system is influenced by so many factors that isolating the effect of galactic environment is extremely challenging. But the basic physical mechanism is sound. Changes in the interstellar environment can affect the heliosphere, which can affect the cosmic ray flux at Earth, which can affect the atmosphere, climate, and biosphere. Voyager's data has confirmed that this mechanism is real and that the interstellar medium is capable of exerting significant pressure on the heliosphere. The 2024 Nature Astronomy study I mentioned earlier took this idea to a new level by providing specific evidence for a dramatic heliosphere compression event approximately 2 million years ago. The study used a combination of geological evidence, specifically the iron-60 and plutonium-244 signatures in deep-sea sediments, with sophisticated computer simulations of the heliosphere's response to encountering a dense interstellar cloud. The simulations showed that a cloud with a density of about 3,000 particles per cubic centimeter, which is well within the range of known interstellar cloud densities, could compress the heliosphere so dramatically that its boundary would be pushed inside Earth's orbit within a relatively short period of time. The result would be that Earth, for perhaps thousands or tens of thousands of years, would be directly exposed to the interstellar medium, bombarded by the full flux of galactic cosmic rays, and potentially receiving a dusting of interstellar particles on its surface. The biological and climatic effects of such an event are still being studied, but the possibilities are dramatic. A sudden increase in galactic cosmic ray flux could increase the production of certain isotopes in the atmosphere, alter atmospheric chemistry, potentially affect cloud formation and albedo, and increase the radiation dose at the surface. The interstellar particles themselves, including dust and larger grains, could affect the upper atmosphere and potentially contribute to changes in climate. Some researchers have speculated that such events could trigger or contribute to ice ages, while others have suggested links to changes in the diversity and distribution of life. The evidence is still accumulating, and the connections are still being debated, but the basic scenario, a dense interstellar cloud compressing the heliosphere and exposing Earth to the interstellar environment, is no longer science fiction. It is a scientifically credible hypothesis, supported by both theoretical models and geological evidence. And here is the truly sobering part. This will happen again. The sun's motion through the galaxy is relentless, and there is no way to predict with certainty what interstellar environment we will encounter next. We know that the local interstellar cloud, the warm, partially ionized cloud we are currently inside, is relatively benign, but we also know, from astronomical observations, that the local interstellar neighborhood contains a variety of different cloud structures with different densities and properties. The Sun may currently be near the edge of the local interstellar cloud, approaching a transition to a different interstellar environment. What that environment will be like, and how it will affect the heliosphere, is one of the most important open questions in heliophysics. Some researchers have suggested that we may be approaching, or have recently entered, the boundary region between the local interstellar cloud and an adjacent structure sometimes called the G-cloud. The properties of the G-cloud are not well constrained, but some studies suggest it may be slightly denser and cooler than the local interstellar cloud. If so, the transition from one cloud to the other could result in changes to the external pressure on the heliosphere, and corresponding changes in the heliosphere's size and the cosmic ray flux reaching the inner solar system. These changes would likely be gradual, occurring over thousands of years, and the magnitude of the effect would depend on the density contrast between the two clouds. But the point is that the heliosphere is not a fixed, permanent, unchanging shield. It is a dynamic entity that responds to its environment, and that environment is constantly changing as the sun moves through the galaxy. I want to pause here and acknowledge something important. I know that everything I've been telling you might sound alarming. The idea that our cosmic shield is weaker than we thought, that the galaxy is pressing against us harder than we assumed, that our protection could be compromised by encounters with interstellar clouds, these are not comfortable thoughts, and I want to be responsible in how I present this information, because it is easy to slip into sensationalism when the science itself is so dramatic. So, let me be clear about what we do know and what we don't know, and about what the actual level of risk is. We do know that the heliosphere is our primary shield against galactic cosmic rays, and that Voyager's data has shown this shield to be more complex, more variable, and more porous than many models had predicted. We do know that the interstellar medium outside the heliosphere is denser and more energetic than some models assumed, and that it exerts real, significant pressure on the heliosphere. We do know that the heliosphere's shape and size respond to changes in the solar wind and the interstellar environment, and that extreme compression events have occurred in the past. We do know that the cosmic ray flux outside the heliosphere is higher than some optimistic estimates, and that this has implications for space exploration and potentially for life on Earth during periods of reduced heliospheric shielding. What we don't know, or don't know with precision, is the exact shape of the heliosphere, the exact timeline of future interstellar cloud encounters, the exact magnitude of the effects on Earth's climate and biosphere during past compression events, or the exact level of risk for the near-term future. The science is advancing rapidly, with new data from Voyager, IBEX, IMAP, New Horizons, and ground-based observations adding to our understanding every year. But there are still significant uncertainties, and anyone who tells you they know exactly what will happen is overstating the current state of knowledge. What I can tell you, with confidence, is that Voyager's data has moved us from a state of comfortable ignorance to a state of informed concern. We now know that the heliosphere is more vulnerable than we assumed, and that the galaxy is more aggressive than we hoped. This knowledge is not cause for panic, but it is cause for attention, for continued research, for vigilance, and for a deeper appreciation of the invisible cosmic shield that has been protecting us all along. Now, if you have stayed with me this far, if you have followed this journey from the launch pads of Cape Canaveral through the storms of Jupiter and the rings of Saturn, past the tilted weirdness of Uranus and the dark blue fury of Neptune, through the heliosheath and across the heliopause into the cold void of interstellar space, then I want to thank you. Seriously. This is a long video and it covers a lot of ground, both literally and figuratively. The fact that you are still here tells me that you care about this stuff, that you are curious about the universe, that you want to understand the big picture. And that means a lot. So, here is what I want to ask you to do right now. If you have found this video valuable, if it has taught you something new, if it has made you think about the cosmos in a way you hadn't before, please hit that like button. It sounds like a small thing, but it makes an enormous difference for this channel. The algorithm, that mysterious invisible force that decides what videos get recommended and which ones disappear into the void, responds to likes. Every like you give this video is a signal that says, this content matters, show it to more people, and I believe this content does matter. I believe that understanding our place in the cosmos, understanding the forces that shape our existence, understanding the fragility and beauty of the pale blue dot we call home, is one of the most important things a human being can do. So, like this video, subscribe to the channel if you haven't already, turn on notifications so you don't miss the next deep dive, and leave a comment below. Tell me what surprised you most. Tell me what you want to know more about. Tell me whether you think humanity will ever build another Voyager, a new interstellar probe that can pick up where these aging pioneers leave off. I read every comment, and your feedback shapes what we create next. Now, let us continue, because we are not done yet, not even close. Let me take you deeper into the science of what is happening at the edge. I want to talk about something that Voyager has been detecting for years in the interstellar medium. Something that is subtle but deeply significant. The interstellar plasma hum. After Voyager 1 crossed the heliopause in 2012 and entered interstellar space, its plasma wave system, or PWS instrument, began detecting something remarkable. Between the occasional bursts of plasma activity caused by solar shock waves propagating into the interstellar medium, there was a persistent, low-level oscillation in the plasma density, a faint, continuous hum. This hum is not sound in the conventional sense, because sound as we know it cannot travel through the near vacuum of interstellar space. Rather, it is an oscillation in the electron density of the interstellar plasma, detected by Voyager's antenna as variations in the electric field. The frequency of this hum corresponds to the natural oscillation frequency of the interstellar plasma, known as the plasma frequency, which is determined by the electron density. By measuring this frequency, scientists can determine the electron density of the interstellar medium at Voyager's location with extraordinary precision. And what they have found is fascinating. The electron density in the interstellar medium is not constant. It varies gradually as Voyager moves outward, and it also fluctuates on shorter timescales in response to passing waves and disturbances. The overall trend, as I mentioned earlier, is one of gradually increasing density, suggesting that Voyager is moving into a region of slightly denser interstellar material. But the mere existence of the hum, the fact that the interstellar medium has a persistent, detectable oscillation, tells us something profound. It tells us that the interstellar medium is not a dead, static void. It is a living, vibrating, dynamic medium that is constantly being excited by distant energetic events, by shock waves from the sun, by the passage of cosmic rays, and by other, more distant galactic phenomena. The interstellar medium is an active participant in the physics of our galaxy, carrying information, energy, and disturbances across vast distances. And Voyager, our lonely emissary, is floating in this medium, listening to its heartbeat. In addition to the steady hum, Voyager has also detected several dramatic plasma events in the interstellar medium. The most notable of these are plasma density spikes associated with interstellar shocks, pressure waves that propagate through the interstellar medium ahead of, or in response to, large coronal mass ejections from the Sun. When the Sun erupts with a massive coronal mass ejection, a huge cloud of magnetized plasma is hurled into space. This cloud expands outward through the heliosphere, eventually reaching the heliopause and pushing into the interstellar medium beyond. The resulting pressure wave propagates through the interstellar plasma at the speed of sound in that medium, creating a disturbance that Voyager can detect months or even years after the original solar eruption. These interstellar shocks provide a remarkable demonstration of the Sun's reach. Even in interstellar space, even beyond the heliosphere, the Sun's violent outbursts can send ripples propagating through the galactic medium. Our star's influence does not end at the heliopause. It leaks through, it resonates, it sends waves into the interstellar ocean. And conversely, the interstellar medium's own disturbances can propagate inward, pressing against the heliopause and potentially affecting conditions inside the heliosphere. The boundary is permeable, dynamic, and bidirectional. It is a conversation between the Sun and the galaxy, and Voyager is eavesdropping. Let me now address one of the most fascinating and least understood aspects of the heliosphere interstellar boundary: the role of the interstellar magnetic field. Magnetic fields are invisible, intangible, and notoriously difficult to measure, but they play a central role in shaping the heliosphere and controlling the flow of cosmic rays. The interstellar magnetic field in our local neighborhood is relatively weak, about 3 to 5 microgauss, which is about 100,000 times weaker than a refrigerator magnet. But over the enormous distances involved, even this weak field exerts significant pressure and has a profound influence on the shape and dynamics of the heliosphere. Voyager's measurements of the magnetic field in the interstellar medium have been surprising and somewhat confusing. When Voyager 1 crossed the heliopause, scientists expected to see a dramatic change in the magnetic field direction, from the orientation imposed by the Sun's magnetic field inside the heliosphere to a different orientation characteristic of the interstellar magnetic field outside. What they actually observed was a change in field magnitude. The field got stronger, but the direction changed less dramatically than expected. The interstellar magnetic field direction was more aligned with the heliospheric magnetic field direction than most models had predicted. This could mean that the interaction between the heliosphere and the interstellar magnetic field is more complex than simple models suggest, with the two fields being draped around each other in a way that partially aligns them near the boundary. Or it could mean that the local interstellar magnetic field happens, by coincidence, to be oriented somewhat similarly to the Sun's field in the region where Voyager crossed. The data is still being analyzed and debated. What is clear is that the interstellar magnetic field plays a crucial role in shaping the heliosphere and in controlling how cosmic rays interact with the boundary. The ibex ribbon, that unexpected arc of intense energetic neutral atom emission, is directly tied to the interstellar magnetic field's interaction with the heliosphere. Understanding this interaction is critical to understanding the overall effectiveness of the heliosphere as a cosmic ray shield, because it is the magnetic field geometry at the boundary that determines how easily cosmic rays can penetrate, where they penetrate, and how deeply they can reach into the heliosphere. Now I want to explore something even more speculative but deeply important: the long-term future of the heliosphere and what it means for the long-term future of life on Earth. We have established that the heliosphere's size and effectiveness depend on both internal factors, primarily the strength of the solar wind, and external factors, primarily the pressure and properties of the interstellar medium. Both of these factors change over time, and both are beyond human control. Let us consider each in turn. The Sun is currently a middle-aged main-sequence star, about 4.6 billion years old, with roughly another 5 billion years before it exhausts its hydrogen fuel and begins to evolve into a red giant. Over its remaining main-sequence lifetime, the Sun will gradually brighten, and its luminosity will increase, which will have profound effects on the heliosphere. A brighter, more energetic Sun will produce a stronger solar wind, which will push the heliosphere outward, making it larger. In this sense, the heliosphere may actually grow stronger over time, at least until the Sun leaves the main sequence. But on shorter timescales, the Sun's activity fluctuates, both in the well-known 11-year sunspot cycle and in longer-term variations that are less well understood. There is evidence for longer period oscillations in solar activity, including possible centennial and millennial cycles, and there have been periods in recorded history when the Sun was unusually quiet, such as the Maunder minimum from roughly 1645 to 1715, when sunspots virtually disappeared for decades. During such periods of reduced solar activity, the solar wind weakens, the heliosphere contracts, and more galactic cosmic rays reach the inner solar system. The Maunder minimum coincided with a particularly cold period in the northern hemisphere, known as the Little Ice Age, and there has been speculation, though no definitive proof, that the increased cosmic ray flux contributed to the cooling by affecting cloud formation and atmospheric chemistry. If such a prolonged solar minimum were to occur again, Voyager's data tells us that the consequences for cosmic ray exposure could be more significant than previously thought. Because the external pressure from the interstellar medium, which Voyager has shown to be higher than some models assumed, would push the heliosphere inward more effectively when the solar wind is weak. On the external side, the biggest factor is the interstellar environment through which the Sun is moving. We have discussed the local interstellar cloud and the possibility that we are approaching a transition to a different cloud structure. But let us think about even longer timescales. Over millions and tens of millions of years, the Sun's galactic orbit carries it through dramatically different environments. Some of these environments could be dense molecular clouds with densities thousands or even millions of times higher than the current local interstellar cloud. An encounter with such a cloud could compress the heliosphere to a tiny fraction of its current size, potentially exposing the entire planetary system, including Earth, to the full fury of unshielded galactic cosmic rays for extended periods. Such encounters are rare, perhaps occurring every few 100 million years, but they are not impossible, and they have likely occurred multiple times over the solar system's 4.6 billion year history. The consequences of such an encounter would depend on its duration and the density of the cloud, but even a relatively brief encounter lasting a few thousand years could have dramatic effects on Earth's atmosphere and biosphere. It is humbling to realize that life on Earth, including our own existence, may owe something to the heliosphere's current effectiveness, and that this effectiveness is not guaranteed over cosmic time. There is even a more extreme scenario that some scientists have considered. What happens to the heliosphere when the Sun eventually dies? In about 5 billion years, the Sun will exhaust its hydrogen fuel and swell into a red giant, engulfing Mercury, Venus, and possibly Earth. During this phase, the Sun's mass loss will dramatically increase, and the solar wind will become much more powerful, briefly expanding the heliosphere to enormous proportions. But after the red giant phase, the Sun will shed its outer layers and collapse into a white dwarf, a tiny dense remnant with a much weaker stellar wind. The heliosphere will shrink to almost nothing, and whatever remains of the solar system will be essentially unprotected against the interstellar medium and galactic cosmic rays. This is the ultimate fate of our cosmic shield, a fate shared by every star and every planetary system in the galaxy. But that is billions of years in the future, and there are more immediate concerns to address. Let me bring us back to the present, and to the question that I think underlies much of the public fascination with Voyager's discoveries. What does this mean for us? Not as abstract astrophysics, not as a concern for distant future generations, but for us, here, now, in our lifetimes. The honest answer is that the immediate direct impact on our daily lives is minimal. The heliosphere is still there, still functioning, still protecting us. Galactic cosmic ray levels on Earth's surface are within the normal range that life has adapted to. There is no need for alarm, no reason to build bunkers or stock up on supplies. The threat is not imminent in the way that a hurricane or an earthquake is imminent. But there are several ways in which Voyager's findings are already affecting human activities and planning in meaningful ways. The first, and most concrete, is in the realm of space exploration. As I described earlier, the cosmic ray environment beyond the heliosphere, and even in the outer heliosphere, is a significant challenge for human space exploration. Voyager's data has provided the baseline measurements that engineers need to design radiation shielding for deep space missions. The data has influenced the design requirements for the spacecraft that will carry astronauts to Mars, and it has informed the risk assessments that will determine mission durations and crew exposure limits. Every future deep space mission will owe something to Voyager's measurements of the cosmic ray environment. The second area of impact is in our understanding of space weather and its effects on technology. Space weather refers to the conditions in space that are influenced by the Sun, and that can affect technology and human activity. Solar flares, coronal mass ejections, and geomagnetic storms can disrupt satellite communications, damage power grids, and pose radiation hazards to astronauts and high-altitude air travelers. Voyager's data on the heliosphere's boundary and its interaction with the interstellar medium contributes to our understanding of the large-scale context in which space weather operates. The heliosphere's overall state, its size, its shape, its effectiveness as a cosmic ray shield, sets the background conditions within which individual space weather events play out. A weaker, more compressed heliosphere means a higher baseline of cosmic ray activity, which means that even moderate space weather events could have larger impacts than they would in a period of stronger heliospheric shielding. The third area of impact, and perhaps the most profound, is in our understanding of our place in the cosmos. Voyager's discoveries have fundamentally changed how we think about the Earth's relationship to its galactic environment. Before Voyager, it was easy to think of the solar system as an isolated, self-contained system, with the sun providing light and warmth, and the planets orbiting in a stable, predictable pattern, unaffected by anything beyond the most distant planet. Voyager has shown us that this picture is incomplete. We are not isolated. We are embedded in a galactic environment that touches us, interacts with us, and influences us in ways that we are only beginning to understand. The interstellar medium is not a distant abstraction. It is right there, pressing against our doorstep, separated from us by a thin, dynamic, vulnerable membrane of solar wind and magnetic field. The galaxy is not just something we look at through telescopes. It is something we live inside, something we move through, something that acts upon us as we act upon it. Voyager has brought this reality home in a way that no previous observation or theory could. Let me now take some time to discuss the future of interstellar exploration, because Voyager's achievements, as extraordinary as they are, represent only the very first tentative baby steps of humanity's journey into the space between the stars. Both Voyagers are, as I have described, approaching the end of their operational lives. Within a decade, perhaps sooner, they will fall silent. And when they do, we will have no functioning spacecraft in interstellar space, no eyes and ears beyond the heliosphere, no way to directly measure the environment that our solar system is immersed in. This is a problem. The scientific community recognizes it as a problem, and there are serious, ongoing efforts to plan next-generation interstellar missions that can pick up where Voyager leaves off and go far beyond what Voyager was ever capable of. One of the most developed of these concepts is the Interstellar Probe, a mission being studied by the Johns Hopkins Applied Physics Laboratory with support from NASA. The Interstellar Probe concept envisions a spacecraft that would be launched in the 2030s and would travel to distances of over 1,000 astronomical units from the Sun within 50 years, far beyond Voyager's current position and deep into the interstellar medium. The spacecraft would carry a modern suite of instruments designed specifically to study the heliosphere's boundary and the interstellar environment, instruments that are orders of magnitude more capable than Voyager's nearly 50-year-old technology. The Interstellar Probe would address many of the questions that Voyager has raised but cannot answer. It would provide a third crossing of the heliopause, at a different latitude and longitude than either Voyager, helping to constrain the three-dimensional shape of the heliosphere. It would carry instruments capable of directly imaging the heliosphere from the outside for the first time, allowing us to see our cosmic bubble from an external perspective. It would measure the interstellar magnetic field, plasma, dust, and cosmic ray environment with far greater precision and sensitivity than Voyager's aging instruments, and it would travel far enough into the interstellar medium to begin mapping the large-scale structure of the very local interstellar medium, the region of space immediately surrounding our solar system.